Now we are. So I'm going to do a few things, including a quick recap of what we talked last time. And the TAs, I told them to come again at around the end, like 8:30. Maybe you have some questions about Elasticsearch and the setup and what they expect from you exact at the demos. So what we have to talk today is, again, the IR basic setup. Then we have specifically vector space models. I'm including here things like BM25 because while theoretically, conceptually, they say it's not vector space, it's actually the formula, if you look at it, it's very similar to the vector space model. Then what we have to talk about today is the language models. And then we have to talk about homework 1 again, and then maybe TA question and answer. At the end, at least 2 of them will come back to see if you have any questions about this. Okay? Again, about this class, it's an easy class compared to, say, algorithms or machine learning. Some of you will take that, I'm sure, right? But the double speed thing, you have to pay attention to that. You can't be late. And about the homeworks, you have to demo. The way you get a grade is by demo your code. We'll require something in the Dropbox folder to be archived for you know, university requires that, so I collect something from you. But the way you get a grade, you show it to the TAs, and if they're happy, you get a grade instantly. If not, they'll tell you what the problem with it is. I want to make sure I'm saying that again, because they're saying not too many people show up to the office hours. That's okay. If you can do all this, everything you said you've done without their support, that's fine. But make sure you actually do it. After the deadline, typically we won't go back and forth. You have a few more days to demo. Like if the homework's due on Wednesday, you probably have until next Monday to show the homework 1. But there's no going back at it. Once you demo, what you have is what you have. That's a great. Okay. So basic setup. I'm going to simplify things for homework 1 in here. We have document collection. And this goes into some organization. Processing. Indexing. So that's what right now Elasticsearch is doing. You send the documents, you have probably a Python script that sends them to Elasticsearch once you set up your index. Right? So now I have the data this way. What we have as a separate step in our homework, but I'm going to include it in here, from here we have a document representation. So I'm going to specifically say D is some sort of representation into numbers, W1, W2, up to WN, I don't know, or K. So I said, I think last time I said big D. So I'm including this here, but in homework 1, this is where you get the TF values or DF values out of the index. So you have to find a mechanism to do that. I don't think Elasticsearch produces naturally those things. Lucene, which is the underlying base of Elasticsearch, will produce things for you immediately. Okay? But you can think of all this, how do I organize my data? How do I set up indexing process, NLP, remove stop words, do stemming, whatever you need to do in advance. Right? And then we have queries, which again are actually, you know, maybe modified or edited. So there are queries from users, and then they actually represent as keyword queries. That's the part where you take a query, and for homework 1, we do this manually. You look at the query, you can edit it, remove some words from it if you want. Of course, if you're at Google, you can't really do manually query editing because you get 100 million queries for like every 10 minutes. So you have to have a big processing pipelines there for your queries. But in homework 1, you are totally allowed to modify the queries. within reason. You cannot add keywords that have nothing to do with the query. But removing things that you think have nothing to do with the content, like document, will, the, all that you can take out if you want. Stemming you can do manually. Now we have those two things, and in here, we pass this to an, say, algorithm or IR scoring function. That's the main objective of homework 1, to implement these TF-IDF and Jelinek-Mercer and Laplace models. So how do you implement that formula given the TF counts and DF and DL, whatever you need from the index, and the queries from the file, right? And that's going to produce a results list. We ask you to format this in a certain way. That's in the homework, the actual format, so the evaluation works. Now, how do we do evaluation? Well, we have the answers, right? So we have the QREL, which are relevance judgments, human judgments. Right? So usually we don't have this file. This is for academic purposes. In practice, we don't know what documents are the ones that's supposed to be retrieved and which ones are not. All the companies have a QA department that verify things every once in a while, right? But typically we don't have the answer. But we do have them for those queries. There's a QREL file in there. So if I look at those two things and I'm running an evaluation script, that's another algorithm, right? I have the answers and I get my results list. So from here I get the performance metric. And for now we're going to just use average precision. In that list, that track eval, this is the track eval program. We're going to look for this average precision number. Later on, we're going to debug that track eval and see what all those numbers mean, but we don't need to worry about that right now. Our worry in homework 1 is here. How do we implement this retrieval function? Okay, so that's the basic setup. That's what we want to do first. Now, our doc collection is 85K, roughly, and it's plain text. Things will get a lot more difficult if that data is not plain text. Web, especially modern web documents, are much more difficult to parse for various reasons. There is a web format to start with, but there's also the fact that web documents don't have a nice body of text all the time. They have ads in between, they have menus, they have links to other pages, and some of them are really complicated that way. So this parsing here that involves parsing and processing the data to start with, it's going to get much harder for documents that are not plain. Now, Wikipedia, perhaps it's easy because it's very well organized, it's very consistent. You can probably write a parser, but it'd be easier to just find one for Wikipedia pages. But for random pages in homework 3, when you're going to say, okay, I'm going to crawl documents at random from the web and try to parse those, a lot of effort will have to go into, okay, if I get a random web page, how do I process it out? Okay? You guys got scared last week? Did I appear as, okay, this is impossible, this class is going to get hard? Honestly, did I give you that sensation last week? Yeah? You can be honest. Because I think some of people dropped, or at least, I don't know what happened, they were just trying. And I'm like, wow, I didn't intend to make it. It's not, as I said, this is an easier class than the other ones you're going to have, just the double speed, that's a little of a wrinkle. I'm not that formal of a person, so you are too quiet for my taste. I'm used to people, either paying attention to me and getting involved and answering questions, interrupt me, being even rude sometimes, okay, if it's for a good purpose. And the other people, okay, I'm not paying attention, so I'm on Facebook chatting, whatever. Yeah, so I'm not a formal. I don't require this church kind of moment where I stand and I'm like the emperor talking. No, we don't have that kind of class. In here, you can just talk like you talk to your friends, okay? I don't want to sound like this is a And as I said, this class almost has no requirements. If you know basic programming, you should be able to do it. All right. Basic setup. So for now, I think it should be pretty easy to set up an index and run the processing, because in Python or Perl, those languages that process text well, it's very easy to read those text documents from a file and send them to the index. That's no big deal. Now Elasticsearch might remove stop words by default, and you have to pay attention to that sort of thing. We didn't discuss stop words and stemming yet formally, so for Framework 1, it's up to you to figure out how to deal with that problem. Either use stop words or don't use stop words. We don't specify. We only did the TAs posted a performance value in Piazza that you need to hit. Yeah. So if you hit that one, it doesn't matter if you use stop words or not, or stemming or not, or which kind of stemming. That's up to you to do back and forth, or talk to your friends and see, okay, should I do stemming? Should I process the queries with stop words or without? On purpose, we leave that vague, so you play with it until you see how it works. So we have this. We have the queries again. We play with the queries manually for a little while to get it down to 2 or 3 or 4 keywords that are actually the keywords you're going to use. Make sure the stemming is in sync. If you think the index has been stemmed, maybe you want to stem the query somehow. Some people in previous years use Elasticsearch as a function to stem the query. So by stemming the query with that function, they made sure that there's the same stemming. They didn't know what the stemming does, but it's the same function, so whatever it did for the documents, it's going to do for the query. Seems like a good logic to apply. We don't know exactly how stemming works, but it's going to do the same thing. Okay? So we are here. Before talking about this, what is a document representation here? So we said a document, I'm going to put 2 things here. There is that document 1, document 2, up to document n. And there is word 1, word 2, up to word d. That's a feature matrix. And you can pick one document and say, okay, what is this document DI? DI is W1I, W2I, WDI. It's a numerical representation, right? A lot of data sciences, data mining, AI, machine learning, will require your objects to be in a numerical format, vectorial like this. So even before you decide what you want to do with that document, there's a processing that says the document is actually an array of numbers. In here, the easiest thing is to have an array of numbers that corresponds to natural counts, right? So we said this last time, this in here, if this is WJ, this we say it's a TF between document I and the word J, and this might be just a count how many times that word appears in this document. This for text is very sparse. It's not always sparse. For images, might not be a sparse matrix, depending how you set it up, but for text, it's guaranteed to be sparse. If we use textual, like unigram features. Now, some people don't use textual features. So for movie reviews, they use the processing, and those are categorical features like genre, for example, for a movie. That's not a sparse features because every movie will have a genre, right? Or the number of sales. Every movie will have some value of ticket sales. So that's not sparse. But if I use word counts, every word will appear in very, very few documents. Every word that's not a stop word. And so there will be, most of the values will be 0, right? So then I need to keep this matrix in a special format to facilitate the sparsity and to use it in a certain way. I don't want to do operations, normal operation, matrix operation with a sparse matrix because I can't represent it in a sparse format, in a non-sparse format. It's too big. Okay. So one thing that we need then, if we have this, now this is not vector space models or language models. This is in general. I need the representation. And this is actually true for all the data sciences. whether it's machine learning or information retrieval, objects will have to be represented somehow. Then what I'm going to say, now to IR, I want to do the same for a query. I want a query representation. So in general, conceptually, I might think about it the same way. A query is kind of query word 1, word 2, up to word D, some sort of values here. That would imply it's represented in the same space. It has D coordinates, numerical. I have document representation, query representation, and a similarity or distance value. Distance function. And we talked about the one last time that's cosine, right? Cosine is D times Q dot product divided by norm of D times norm of Q. There are many similarities and distance functions, hundreds of them. In principle, you can use any one of them to measure this. If you use a similarity function like cosine, is cosine a similarity or a distance function?
Similarity.
So it's big when things are similar. So, you sure?
Cos 0 is 1, cos 90 is 0.
Okay, so it's not a similarity. Similarity means it's big when the things are similar, right? Is cosine that way? Is it big when things are similar? Let's think about that if we're not clear. If they are similar, two vectors, what does it mean similar? Similar means, in a vectorial sense, they get one is here and the other one is here, right? That's similar, they in the same direction. So similar for us means small angle, right? This angle is small. And small angle corresponds to what kind of cosine? Big cosine. Big cosine. And non-similar, it's like one is this way and the other one is that way, right? That's a big angle. And that means small cosine. So is cosine a distance or a similarity? Is it corresponds to similar things, bigger values, or similar things, smaller values? Similar things, bigger values. Cosine is a similarity function for us. Okay. We also talked a little bit about why this is appropriate for text. We had this issue with how do you want to measure the text in terms of content. If somebody copy-pastes a document to itself, say 2 or 3 times, geometrically, what would that mean? Geometrically, if I take the vector and I copy it again, I'm doubling all the counts, right? Or tripling all the counts. So if I do that, now this is the document, this is twice the document, and this is 3 times the document, right? Cosine works nice that way because it doesn't change. Cosine is a function of the angle. By changing this anywhere, putting my thing on this line, right, unless I go the other way, the angle doesn't change. Therefore, the cosine won't change, which means if I copy-paste the document to each other, or the query to itself, right, I don't change the angle. The similarity will be the same. That seems to match, I think, our understanding of documents. If I double a document, I don't change its meaning, right? It's the same kind of meaning that it had before. It's, of course, this is ideal. In practice, longer documents are not duplicated of each other, but it has this nice feeling of if something is proportional to its length, right? It's that proportion that matters, not the actual count. Okay, so I can use cosine here. And then, what are the representation? What are those values? So I have now a basic function that I can implement in text. What are those values? So when I say document is W1, W2, WD, I can have a TF representation where I or J is the TF on the document of word J. Let me just write that in words. Word J. And then we have a TF IDF representation where this value that I'm putting there numerically is the TF between the document and word J, but multiply with the IDF of the word J. So that's something that doesn't depend on the document, it's a rarity function. I want this IDF to be high when the term is rare, and to be low when the term is common. So stop words should have an IDF of very close to 0, right? If I use that, I may not have to remove stop words manually or do something specific for stop words, right? If the IDF ensures that stop words or very frequent words have a 0 thing, it should come out in here without me worrying about the stop words at all. Right? What else I can use? I can use this or copy TF. I mean, even add IDF to it, right? I could say that value is, what is a copy TF? Is a way to asymptote, to make the TF non-linear. That stands for a non-linear TF. Because TF is a linear function, right? It's for each count gives you one more unit. If you see it 3 times, it's 3. If you see it 6 times, it's 6. So in terms of inside the formula, if a TF value is 3, it's going to be half of what is 6 because it's acts like a product here. It's a linear function. So how do I get the non-linear TF? There's all kinds of functions. I'm sure some of them mentioned in the slides. You can pick whatever you want. I think it's something like TF plus. Wait a minute. Let's do one that's real here. No, I have one here. So TF, that's the same as before, plus PF plus, I see here 1/2 plus 3/2 times document length divided by the average document length. You'll be surprised with how fancy heuristics people come up with.
Yeah. I had like a vocabulary question. I'm not familiar with all the vocabulary. So corpus is just all the documents, and then collection for unigram LM with Laplace smoothing. I think that means that it's just talking about, like, if I have a query, it's all the tokens in the query, that's the collection, that's the vocabulary, but I'm not sure.
Vocabulary usually means the vocabulary of the collection.
Yeah, I don't know what you mean by collection.
You mean the homework in there?
Yeah.
Okay, so I can go back to the homework in a second.
Okay.
Usually when we say vocabulary, we mean the vocabulary that's encountered, which is all the words that you have seen. It may include the queries and the documents, but typically it's the document collection. If you see, I have to go back at the homework to see exactly what you mean, but in general, if there's a query word, like a keyword, that's not observed in the collection, it's pointless to try to match it. We don't talk about fancy AI in here that will look at the word that you have not seen and tries to figure out what that word is. Like Watson, IBM systems that go figure out what it is. We're not doing that, at least yet. So if you see a word in a query that you don't have in the whole collection, you can safely ignore that word because it won't match anything. So by vocabulary, we typically mean what we've seen in the index. Is that answering the question?
Well, I was confused about the word collection, not the word vocabulary.
So collection refers to a set of documents. Vocabulary refers to the set of unigrams that you see in those documents.
Okay.
But I have to look to make sure I understand your question. I'll put it up in a second. Okay, so what is this? Well, first of all, who TF is the count, like before, right? This is some constants. Who's DL? Document length in What length counts? What do we, when we say length 25, means 25 words, right? So that typically requires a parsing that breaks by spaces and dots and question marks to break it into words, right? Separators, natural separators. And who's ADL? Average document length, that is, take all the documents and compute some sort of average. I can tell you right now that some people in the previous classes, they think that this works better if they impose an average document length. Instead of taking all the documents and average them by length, they came up with a number ADL here that's not the average document length, but it's still one constant. And they figured out that the average document length might be 100, say, but this whole thing works better with like 200 put in there, something like that. So people have tried to fix this. And this is just a heuristic. Let's look a little bit at its behavior. What happens if TF goes very high? So compared to the, TF will never be higher than document length, right? In fact, it can be more than, I think the most frequent word in English is the word the. It's about 1/7 of the English word. Every 7 words you see a the. But some people who span things, they could put a short text, like 2 sentences, and then 3,000 repetitions of some word that they want to spam with. So it is theoretically possible in a document that's length 5,000 to have 4,900 occurrences of one word. That means TF will be roughly the DL. So what would happen in that extreme document where the DL is 5,000? It's about 10 times more than the average. The average document say it's 500, but this spam document is 5,000. So this is 5,000. This is almost 5,000 because it's a word that's being spammed. It's put in that page repeated 49 times, right? How much is this thing? This whole fraction. So TF will go again with TF with a DL, right? This becomes 0 because it's 1/2 divided by x. So I'm left with 1 plus 3 times 2 500s, right? Is that right? So how much is that? Are you guys following me? I'm trying to come up with this extreme document that's much longer than the average document. It's a spam document. And the TF value, it's almost close to DL because there's a word repeated. So if I do that, I'm going to get 1 after I divide with the TF. Rather 1 plus 1/2 TF. So I'm dividing the whole thing with the TF. Plus 3 times 2 ADL. So what is this value? This is almost 0. This is almost 0. So this is close to 1. So I think the purpose of these formulas, there are many variations of it. You can try something much simpler without ADL on the bottom. Is to say, if a term becomes dominant in that document, I was using a very extreme example of dominant. That's not an actual English document. But if a term becomes dominant, it can only go that high. This whole value, my representation value, Wj for that document, is not going to be bigger than 1, and 1 will be achieved only in extreme examples. What happens if I have a very large document, but the TF is close to 0? This is a very rare term, the word, atomic, and only appears 1 in a very large document. How would that look? I have 1 that's without simplified. That's division by TF, but without simplifying that TF. TF, it's a 1. The word appears only once. That's 1 plus 1/2 plus 3/2 DL divided by that. So that's a long document. So the ratio between this document and the average document is 10. It's a long document. The term is rare. So this is be roughly what? This is a 15, 16, 1/16 roughly. So I think those are kind of extreme examples of how to get this particular value Wj high versus how to get it low. I think those are the extreme examples. So you can say the lowest one is probably 1/17 in this heuristic. The highest one you get is probably close to 1. That's in a spam document that's very long. I keep saying this is a heuristic, and that means you can play with those formulas. You're very welcome to play with it to see if you can get a better performance out of it. So those constants are not big theory for how people have got those constants. They just play with it until they find some constants that generally work. It may be for different data sets that use different constants. TAs have access to previous Piazza posts from previous years. So there's all kinds of trials and errors in those posts, what students have tried and what worked better for this data set versus the default value, so on and so forth. But we don't want to give you this value in advance. You can play with it until you hit that threshold that has been posted. It's easy for TF-IDF systems to get that threshold. It's going to be a little harder for language models to hit the threshold. So I think it's, I forgot, is it 0.15? And this is, okay, the 0.2 it's easy to hit for these systems. The language models to get to 0.15 it's a little harder. All right. So if I want IDF, I can still add the IDF here. That's just replacing the TF with something more asymptotically curved instead of being linear, but I can add IDF too. Now, whatever the representation I use, I can still do this. So this formula or other similarities, I'm just putting one. I could use an Euclidean distance or some other distances. I could use them independent of how I choose to represent the document. So I think we should establish today, if we didn't establish last week, that representation is relatively independent or separate, let's say, to the what scoring function I'm using. I can use different representations with different scoring functions. Now, those things are not quite independent. Some similarity values work better with some representations. So it's not like any representation works equally well with any scoring function or similarity or distance functions. Right? That's another thing that you have to play with. In this homework one, you have options for representation on the documents. You can use simple counts, IDF with simple counts, IDF with Okapi TF, and there is that crazy formula that I don't want to really talk about. There is another big heuristic that people have played with. BM25 formula, if you look at it, also looks kind of like that. I don't want to write on board, but when I put the projector up, I'm going to talk a little bit about that formula. You can look at a formula and say there is a document part and a query part in it. It's just a different kind of representation for documents. They have more constants to control the asymptotes. So what do we have here? I think we want you to play in homework one definitely with the representation to try to get different vectors for documents, see how they react. You can, I don't think this homework requires you to change much the formula here, but you could. BM25 is not exactly this formula. It's something very, very similar that you may have to modify a little bit. Now, how do we implement this formula? Once we have a representation for documents, we said the query representation is just a bunch of ones and zeros. So every word in here is 1 if the word belongs to the query, and 0 if the word does not belong to the query. So we don't use counts for the query because it's very unlikely in web search, say, a query to contain a word twice. And even if it does, it's probably a typo. It's not intended to be duplicated. So if I use this, what is this formula becomes? dq divided by d times q. What is this? We said this last time, right? That's going to be 1 over the document length. The query, I'm going to put here on this, sometimes we say this in ranking. Ranking on an equal sign means not equal. It's the same ranking, but it could be different scores. So this transformation that I'm doing here won't affect the ranking, but you may have different scores. So if I have to sort the documents by this, I get the same ranking list. So that will be sum over the words in the query of, say, the document representation of that word. because the words in the query are the ones that have a unit value, and the ones that are not in the query have a 0 value, so they don't appear in the sum. Who's with me so far? Questions? That's actually what we talked about last time, more or less. We're not picking how do you guys implement these formulas. So I think Thais might ask you about the document representation. Do you have idea? If you don't have idea, how do you asymptote DF? But how do you implement a particular, cosine or Jacquard coefficient or other similarity function? That's okay. Any such thing that's a formula looks like that will pass for the homework if it gets you the performance that you need to get. Okay, so one important point here, when I say words that are in part of the query, after query processing, I'm essentially ignoring any word that's not part of the query, right? So I'm going to say that right here, ignore words that are not in the query. Can I actually do that? Like when I implement this system, can I write this whole thing only by looking at words that are part of my query? So my query is nuclear bomb. Okay? Can I do everything here by only looking at the words nuclear and bomb and ignore all the other words? What I cannot do. So can I, assuming I already have the index, Elasticsearch index, that's built in with all the words, can I just say, okay, I only care about the query nuclear bomb, so I want to implement my scoring function here, only looking at the words nuclear and the word bomb. I don't want to do anything with any other words because they're not in my query. Is it something that I'm missing?
Yeah, document links.
Maybe document length. That would be one thing that I need to worry about, because if I look at nuclear and bomb, I don't get the document length out of those things. But I think in principle, most of this stuff can be done just with the word nuclear and the word bomb. And another thing is, when I look at this scoring as an accumulator, is a sum, if a document does not contain one of the query terms, so I have a document that contains only the word nuclear but not the word bomb, the effective value for the missing word is 0. Because it just sums over documents in the query, and if the word does not appear in the document, can I say every word that does not appear in the document gets a 0 value? Would that be a true statement? Let's look at these formulas. If it's not appear, would this be 0?
Yes.
How about this?
Yes.
How about this?
Yes.
You sure?
TF would be 0.
Okay.
TF would be 0.
But there's some other formula for copy TF that's TF plus K. Would that be 0?
Almost.
But not 0, right? So you got to be careful with this representation. Some of them maintain the 0, no word means 0. So that way it's easy to think about it. If I don't see this word, even though I change the actual TF values, it's still a 0 when it's missing from document. But some formulas, if it has something in the numerator, they actually change the 0. Even though the TF is 0, now the value is not 0 anymore. That will actually be a big deal in language models. I think in these kind of models, you can get the results with just this formula, and then effectively saying if you don't have a word in a document, you can skip it. You don't have to worry about it because the 0 is not going to count for anything. Okay? And then we said for the TF values, TF IDF systems, AP, we wanted at least 0.2 average AP. So that has a name. It's called mean average precision because it's over queries, at least 0.2. All right. Let me see if there's anything else I need to worry about here. We also talk about something that we do as extra credit that is, there's no points for it in the class. There's no grade improvement, but it's something that you might be interested. That is, suppose I want my representation to not only contain values that are each, this is a value per unigram. So this is one value for each unigram. That is the number of dimensions is the number of words. Of course, I can use bigrams. We talked about this last time, where I have a value here that might be a value corresponding to a bigram, and we said there's a difference between a bigram and two unigrams, because two unigrams, there's no distance between them. If they appear Virgil and Pavlu, two parts of the document, they still count as so many Virgil with a tier value and Pavlu separately. A bigram would only count as bigram as a non-zero value if the two words are close enough in text. And the fancy version of skipgrams, they actually are not black or white. They count occurrences based on how far away the words are. If they're really close together, like Virgil Pavlu, that counts as a one occurrence. But if they start being far apart a little bit, that's like half of the occurrence. And if they're more far apart, that's 1/3 of an occurrence. And if they really far apart, maybe that's 1/20th. So they say it's there, but it's really far apart. Probably they're not related. It's just accidentally in the same text, right? So the version of bigrams that's interesting is the one that's called skipgrams, that accounts for the distance between the words. Not black and white. Accounts quantitatively, as in the farther they are, the less value it gets. There are some very fancy machine learning kernels for text, they're called, that implement these distances between words, not just for two words like bigrams, but for trigrams to fourgrams. And Elasticsearch has some built-in functions that allow you to control matching. When you say I'm putting the query, say 3 words, how much loose do I want to be with the matching? How many words do I allow to be part within that span? That still counts a match. If I want to be really tight, I'm telling it I want to match those words as one after another. There's no words in between. But if I want to be really loose bigrams or trigrams effectively go back to unigrams, because if they're very loose, they effectively anywhere in text they count as occurrence. Makes sense? So I think some students that had more time to put into this class after they finish the homework, they're really interested into how do we do bigrams or trigrams. The implementation of these functions, it's a little tricky. Why? So far, we assume, like machine learning sort of thing, that the document representation can be designed in advance, right? That's the way, I think our implicit assumption here is that you get a collection of documents, 85,000, you index them, process them, do whatever you want, but at that point, when you're done, this is settled, what the document representation is. And then when the user posts a query, you use that representation that you already have. So that's nice because you can do as much time as you want as in pre-processing, right? It won't affect your running time speed. But when you're down to the query, you don't need to reprocess the document. The problem with, say, bigrams or trigrams is that it's kind of hard to do all this in advance. It's not impossible, but you can't. It's hard because there's the dimensionality for trigrams could be in the hundreds of millions, if not larger. If I am to really represent all the possible trigrams with matches, there's a lot of them in English language. So some people have thought, how about we don't represent in advance all the documents with bigrams and trigrams? We still represent the unigrams, which is easy, because for unigrams, this D is maybe 50,000 or so. But then when I put a query, and I need to match a trigram, the matching becomes more complicated because I don't simply have a formula that takes the query times the document. The document representation in trigrams have to be figured out. It's not already part of my data structure. So I do have the unigrams and I may have the positions, which allows me to recover bigrams and trigrams. But because it's not done, how to do this efficiently at query time. How to say, okay, I have a unigram representation, but I want to do a bigram matching. So I have to figure out in real time what bigrams matches. That's actually tricky. Because you don't want to spend the query time, a long processing time just to figure out these bigrams, right? You still want to go by the inverted list to say, if the query is nuclear bomb, go for those words only now I have to check the positions to be close enough. So since I'm talking about this now, I want to show you that we may have to go back to this thing again. So there's few extra credits that I'm going to talk a little bit about, but then I'm going to talk to you guys more at office hours for the people who are actually interested in implementing them. But I want to mention in class what are about. Actually, maybe something that is out here. This is one of these moments where I don't know what camera is actually recording. If you go and take a look to see what's in there, hopefully put this down. How did we pull it down last time? I think it's the boards, right? You just move the boards out of the way. Okay. I don't know if you think the camera is recording okay. See the. So there's a guy at Microsoft. Yeah, I'm gonna turn off the lights here. There's a guy at Microsoft who figured this out, and his question is exactly this: if I want to do at lifetime, at running time, I have only the unigrams with positions, and I want to match a skip gram. How do I efficiently, once I pull the inverted list, I have nuclear, bomb, atomic, commission, and I go for each one of them, I get the documents that contain those unigrams with counts and positions. Because that's easy, it's in my index already, right? How do I now figure out what spans a lot and what spans little? So his question is this: suppose I match 3 words. That's different than my example. Cheap padding and pops, right? These are the positions in one document. 0, 5, 10, 15. Positions are by words, right? This 0 means is the first word. 1 means is second word, so on and so forth, right? So I have this list that can be how many times cheap appears. If it appears 20 times, there will be 20 positions here. Right? What am I looking for? I want to see where it matches tight. Tight means what? Close. So I want to match all 3 words, but as tight as possible. So tight means the difference between the smallest position value and the highest position value to be small. What's the smallest possible if there are 3 words?
Next to each other.
What?
Next to each other.
So what's that in this case?
0.
Is 0, 1, 3 valid? No, because it has to match all 3 of them. So what's this?
5. 0, 4.
0, 4?
3,
3, 4, 5. Is that the most tight possible?
Yeah.
Yeah. Because the distance between the minimum and maximum is 2, and that distance is necessary for 3 words. Hands up who's following me here. That's the problem statement. That's what we want to get. Anybody knows an algorithm? I use this, by the way, in one of the algorithms exams. You have k words. These are the positions matching in text. Your job in an algorithm, that's pure algorithmic problem. Find me the 3 occurrences, one here, one here, one here, that have the shortest span. May not be 2, right? If there's no occurrence with them tight one after the other, maybe the minimum span will be, suppose this 4 is not here. What's the minimum now? Without this 4. The word 4 is not pops, it's something else.
8,
8, 9, 10? Okay, suppose 9 is not here. 0, 1, 3 is not valid, I think, because it doesn't include this. You have to include 1 in each line, right? Because you need a,
5, 6, 8.
5, 6, 8 is just allowing how many extra words in that span? It's one more word. 5 is one of them, 6 one of them, 7 is some other word that's not here, and 8 is the last one, right? So how do I design an algorithm that finds me the tightest span, assuming I have these occurring positions of all those words? I want an efficient algorithm. Now I'm at runtime. I can't afford to do a lot of computation. It's not the pre-processing time where I can stay overnight, index these documents, deal with them. I actually have a user query. It's cheap padding pops, right? I have the inverted list. To get inverted list, it's easy. I call the index, I get back the inverted list. It's almost no computation because that's the whole point of the index, to store those things in a format like this. This is one document only. So how do I go in here and find out the fast way to get that span? So that's what this blog is about. And it says, sort those each list. It's already sorted in increasing order. All the positions are stored like that. Start with 0, 1, 4. Keep track of the current span. The current span is 4 minus 0, size 4, right? Advance the smallest value. That's the 0, right? So advance it to 4. What's the span now? 1, 5, 4. The span is 5 minus 1, 4. Advance the second, again, the smallest value. So that's 1, right? So advance that to 3. Now I get 3, 4, 5. Now I can stop because 3, 4, 5 is the best possible value I could get anyway. But in practice, we may not find the best value, so we might have to keep going. And then if we keep going, advancing all the values, always advance the minimum value and check the span. By the time I'm at the end, this algorithm, this blog in here says, if you do this, you only do a linear traversal because every time I'm advancing a position. If I have in here 20 numbers, I'm only advancing 20 times total, so it's linear. And it's not possible to miss that title span. That's not an obvious statement because I'm advancing something and then something else, and then something else. How do I know that the minimum possible span was not something that I skipped over, right? Like if I enter the minimum span with one of the pointers and I keep advancing this one before advancing the other one, I may miss that particular position. I mean, hypothetically speaking. So the point of this blog is that doing this, it's a linear algorithm, and it's not going to miss that tight span. Obviously, you won't check all the possible spans. All the possible spans will be m times n times p checkings. That's much more than linear. If this is 10 times 10 times 10, that would be 1,000, as opposed to advancing the pointer 10 plus 10 plus 10 30 times. So it is an efficient algorithm, and it's not going to miss that minimum span. So there are ways to implement things like trigrams this way without storing in advance all the trigrams in my matrix. Questions? This might be useful for other things in algorithms, not just for the general problem of finding the closest three objects in a tree list, the closest three positions. I think it may be applicable to other problems than just trigrams in information retrieval. By now, I think the systems got so powerful, the computational systems and memory, that bigrams and trigrams are pretty much stored in advance. But there's still a question of general n-grams. If I want to go to n equal 5, that's not possible to store in advance. There's just too many n-grams. And in different languages, I may have to go further than 5, depending what my unit of matching is. Okay. So that's one thing I want to talk about extra-credit. The other thing that people have done quite a lot, and they still do actually, even in practice. Let me see if I have a short slide set in here. Maybe I use that. We'll go quickly over this. I'll talk about what's about, but I won't go over all the slides. This is something that was a big deal both in research and academia. This happens to be published by somebody at Northeastern. That's not me, but it's somebody who works in information retrieval, a researcher, about, I don't know, 2003, so say 15 years ago. They're not so fashionable, so hot anymore, but they used to be a big deal. And they still, it's how actually search engines work. We'll get there towards the end of the term, exactly what I mean by that. Here's the deal. You can imagine the meta search problem being, I'm putting a query and I'm getting 3 sort of results, either by 3 different algorithms, like maybe the 3 systems here. Those are so old that Alta Vista was still a thing back then. So I could, because those systems implement different retrieval functions internally. It could be, I mean, I don't know what they implement. I'm just saying they could implement different things. Or by other reasons, maybe they look at different collections of documents or who knows what, right? So that's actually what you guys are going to do, because you have 5 systems in homework 1. So you can say, I'm putting a query and I'm running all 5 systems. Each system returns a list of results. Presumably might be different because the BM25 might sort things differently than the Jelinek-Mercer language model. When I said there on the board ranking, I say 2 scoring functions are ranking equivalent if they sort things the same way. That's always true for monotonic transformation. Like if I take a scoring function multiplied by 3, I get an equivalent ranking function. But language models and TF-IDF are very different functions. They're not monotonically ranking equivalent. So you could get different ranking systems. Even commercial engines, the commercial engines have this problem straight off the bat. As soon as you put a query, they have the problem. It's not different scoring functions. What do you think Microsoft is going to do when you put a query? Essentially, I'm saying Microsoft will have few rankings before showing you the results. Why Microsoft, Bing, or Google will have different rankings, and not just 3, probably like 600 of them.
Different document collection.
No. I mean, that could be it, but it's not the case on General Web. General Web acts on tier 1, it's 1 billion documents. Why would they have, before showing you because you only see 1 list, right? Bing will produce 1 list for you. Why would they have 600 internal lists? They based on different, yes, 600 scoring functions.
They probably have a number of models that are tuned for specific use cases, like specific types of results.
Specific criteria, right? I can have something that ranks for entities. I can have something that ranks by content purely, like if there's words like nuclear bomb, those are very, very specific words, so I'm doing something with them. I could have something that looks at I don't know, particular websites like Wikipedia or news documents, right? So that's actually happened, and it starts happening from this research. This research is what ignited this whole thing of, before I'm showing the user the results, I use all my criteria rankers, And as it happens today at Google, at least, I'm more familiar than Microsoft, because some of our students are actually software engineers at Google, so now we understand a lot better how Google works for the people who took IR 10 years ago from our department. What happens is they don't even know where those things come from. They have different teams, and teams work on a ranker, right? So you're a manager, you see 600 rankings. You don't know, okay, how did this guy implemented that ranking? Like, who knows, right? All you know, it's consistent. Like if you put 3 queries and you call that team to give you this particular ranking, they will use the same function to give you this ranking. So internally, this is what happens. Some of the rankings are pre-processed already. So as soon as you put a query just by your IP, or just by some simple analysis of the query, some of these 600 rankings are pre-processed, and some are based on the query, like they have to pull the index and do some scoring on it. Those 600 rankings get into a meta search model to produce the list that you are actually seeing on the screen. Now, this is the old stuff. The new stuff is all machine learning. So the new stuff doesn't have any heuristic and combination. It trains over these 600 ranks as features with the QA output, what's good and what's bad, and it learns how to read those inputs as features, the 600 model, to produce the list that you see. That's purely now based on machine learning, but 15 years ago it was not. So this is how initially people have thought of this problem. That is, I'm having the list of documents. Let's say they have the same documents in different order. I want to produce a meta search list. And I don't want to bother myself with the scoring function of each one of those. So I'm assuming I get the lists, but I don't know how they were produced. Does that make sense? So I'm the manager now. My teams, each one of them produces a list for me. I don't know the scoring function, but I get to see the ranking of those documents. So what should be, say, a natural criteria to say, when I know a document should definitely come up on top, independent of how the lists were produced? It's high in all the lists, right? So document appears high in all these lists. Presumably all those teams were well intended. They will put a document that they think for some reason is good. And we don't know that reason, we don't know the scoring function, but if a lot of the lists produce the same document at the top, that should probably go on top, right? Well, that's easy if those lists will be the same ranking, but at some point they're gonna differ. They're gonna have different rankings. So what do I do, right? I have some document that's higher in this list, but lower in this list, and high again in this other list, and lower, and I don't have just 3, I have 600 of them. How do I decide what document I'm gonna list? It's easy to say if a document is high on all lists, it has to be high in this list. If it's low on all those internal lists, it has to be low in here. But what about in the middle? Some documents are high in the list and low in another list. Come up some weighting function based on ranks. Do you know of any other process in our society that has this kind of flavor? People rank things. They don't call it ranking, but that's what they do, and they have to come up with some sort of list.
Voting?
Voting. And voting, it's old. People have thought of voting for a long time, right? So they come up with heuristics for voting. Now, in some voting systems, it's easier. Like in the United States, a congressman or a senator is directly voted by the majority in that unit that is the electorate in that whatever the region is. But in some systems, like in France or in Europe, in some countries, they have to count the votes cumulatively over the whole country, and there's different ranking criteria inside the city, inside the region, inside the country, and then they have the second round of voting and sometimes the third round of voting, so it can get complicated. So the idea of weighting ranks to come up to combine several criteria into one, it's not new. It was discussed in voting and some other systems before. So this is a slide that presents some of these algorithms. I will go pretty fast through them. So here's the basic version. This one says, normalize to have the same list. It assumes that we have a little bit more than the list. We don't know the criteria and we don't know the scoring function, but we have the scoring value. So each list comes with a bunch of scores. It's not just the ranking. Whatever function has been used, is that clear what I'm saying? Whatever function has been used, I have a scoring function for each document. So I have a scoring value, even though I don't know if it's TF-IDF or BM25 or something, I have the score. So what this system does here first, MNZ, it normalizes the scores and sum up the scores in each list. That effectively ignores the ranking and says the total sum score of a document cumulatively is the sum of the normalized scores in the internal systems, maybe divide by the number, but that's ranking equivalent if I divide by the number. I come up with a sum score and then I rank by that score. M and Z, which is a variant of this, it does another little trick. It not just does this, it normalizes the score, sums them up. It also multiplies with the non-zero, number of non-zero things, which essentially says how many systems contain that document. So it takes the sum score, and then it says this document appear in 348 out of 600 lists, because not all lists contain all documents. So if it's 348 out of 600, it multiplies to 348. It says 348 things contain this document. If it's only 3 of them contain the document, then it multiplies by 3. So multiplies by how many lists actually produce the document. Does it make sense? I don't know. To me, when I heard the first time this, that was 10 years ago, I was like, what? Right? Like, who came up with this? You'd be surprised how well things work that people came up with over the trial and error periods, and they don't have a theoretical justification for it, and yet they work so well. COMB MNZ is a meta-search algorithm extremely hard to beat. People have tried for 15 years now to come up with simple schemas, non-machine learning, to overcompete with this. None of them work better than COMB. Machine learning did. But every other heuristics, and over the years, if you type meta search or fusion of lists in IR, you get at least 3,000 papers in the last 10 years that talk about this problem. And every single paper will have MNZ as a baseline for non-machine learning systems. So that's something you guys can implement. You run those 5 systems, you can run other 5 more, and now you have a ranking of your query documents for a particular query. This is per query, obviously. And then you can do COMB MNZ on top of them just to see if your fusion list is better, because you can run track eval on the fusion list to see if that's better than the internal ones. By the way, the purpose of meta search is not that the final system to be better than all the incoming systems. That's kind of hard. The purpose of meta search is that the meta search output list should not be too far away from the best systems. The problem people have is, I have 600 ranking criteria, and I got 600 lists. Now, some of them may be good, and some of them may be bad. The purpose of meta search is not to beat all of them, is to make sure, is to somehow not beat in the bad ones, right? You don't want to pick one of the 600 and output it as a list, because that may be terrible for some users. So I think meta search has always been compared. Out of these 600 systems, we can measure performance on each one of them individually. We want the meta search system to be at least the median of them, to say, if I output a meta search, I won't be as good as the best one all the time, but I will be better than the worst one. That's how people have thought of evaluation of these systems. It's more of a safe procedure to not return bad results by missing the criteria, rather than trying to match the best system. What else can we do here? So they compare with these track data sets. Condor said this has been, I think, designed as an election system, actually, if I remember correctly. But I don't think this is the one we talked about here. This is a Bayesian. So another thing is a Bayesian strategy. It's not really a machine learning system. It's a way to say, that's something I'm going to talk right after the break. If I go and decompose this document into what I think relevance is coming from, where is good and bad, what makes a document good and bad, can I use a Bayesian approach to kind of combine those lists? So the idea on the Bayesian approach is if I go to this list, let's say I have a list of documents. I'm going to try to say if this is better than this, right? If this document 1 is better than document 3, how many of my lists, this is document 1 here and document 3 here, and this is document 1 again at the top and document 3 here, and this is document 3 here and document 1 here. In how many of those lists document 1 was ranked higher than document 3? If all the lists have document 1 higher than document 3, I'm going to ask in the output list also to have this property. Document 1 should be higher than document 3. I'm not specifying where in the list, but I'm saying it should be higher because consistently that has been ranked high. So this is where it gets to like in election systems. If all the people would rank a candidate higher than another candidate, it's easy to say in the output D1 should be higher. But if some voters rank this one way and some voters rank this the other way, it gets to a problem where I have to combine results. So this Bayesian approach is here. That's one of them. Let me see the other one. Election strategies, that's the other one. So I don't want to go into the details, or we could at office hours. So one is Bayesian, the other one is election, and the other one is very simple election. Let's say it's called Borda, for a French mathematician from like 150 years ago or so. This guy said something very simple. We're gonna use the ranking. We don't have the scores, we don't have access to the score function. We don't know in each list how the score was produced. We're gonna ignore the score. And we're just gonna look by the rankings, and we're gonna cumulatively look at rankings. So what rank do I have here? 1, right? What rank is this one? Maybe rank number 5. What rank is here? Rank 1. And here is rank 10. So what Borda says, I can sum up 10 with 1, with 5, with 1 for this document. This is the same document. Would that count as a penalty or as a reward? Like the higher this value is, the better or the worse?
The worst.
So it considers the ranks as the scores effectively, sums up the ranks, and the document with the minimum score is the one that has the top ranks overall, right? So that's essentially like COMB-M and Z, but instead of summing up scores, which we don't know, because now we say we don't know the scores, it sums up ranks. So that's something extremely simple that you guys can implement. You look at your systems, 5 or 6 or how many you implement, you attach for each document, what are my ranks in each of the 6 systems? Rank 1, rank 3, rank 7, rank 25, 85. Sum them up. Whoever have the smallest sum of ranks gets to be in the output the first document, second, third, that's a scoring function, so that's simple. For this election and base, you have to read some of these slides, and if that's not enough, we have to dig up those papers and see how they implement it. Okay. Here's Condorcet voting. That's an election strategy that says you may have this paradox that in terms of preferences, A prefers, one voter prefers candidate A, then B and C, another voter B and C and A, another one C and E and B. So there's no fair way to break some cycles here. So this goes into a graph theory problem that says if I represent all my documents in a graph and I start putting arrow, this has been listed higher than that. That's an arrow, and so on and so forth. I transform this into a graph problem, and then in graph I'm saying, okay, what is the vertex to the maximum owl degree or the maximum dominance to the other ones? There's all kinds of graph properties, and then use something like that to rank it. None of these methods manage to beat COMB-M and Z without machine learning. So I can tell you right now, everything that's not using machine learning, none of this stuff, we don't think this Bayesian strategy is a machine learning strategy. But out of all of them, the simple one is sum the scores multiplied by the number of non-zero systems, like how many systems contain that document, it's still king of the hill. So it's hard to beat that one with simple strategies. I don't think we have anything here other than that. So we have a bunch of papers from all these past 10 years that deal with metasearch problem. I only want to make two comments. It's an interesting experiment to do once you have those, how many systems you have. It doesn't work very well with 5 systems, but if you can produce 15 systems or 20 or 25 systems with variations, then it makes sense to try to combine them. And the other comment that's important here is that in commercial systems, this happens all the time. They have a lot of internal rankings, and then they have to combine those rankings somehow, but they use machine learning, not heuristics like this. I think with that, I think we can take a break now, and then after the break, I'll talk about language models, which is the other part of this homework. And then the TAs will come towards the end to see if you have any questions about Elasticsearch or the setup. Okay? How's summer going so far? Homework 1 will be done by Wednesday. I think I scared too many people off last time. No, I think because they dropped the course. They were 50 now, we only 30 something in this class. I don't know. No, we use Elasticsearch to index. That's conceptual. Now, when you pull out values in the tables, you can pull them out in advance in hash. Well, that's not what you do, right? In practice, you pull it from an index or from data source.
We just use no more happens. You know that if you have a hash, you can have a hash that's very completely applicable, then you can grab your documents again. That's really not that about the at least your code that I mean is going to be that's how it's
But it's not at least because for each query, you have to pull different things, right? For a query, you get, you can't store the whole hash. I mean, the homework tool is exactly about this. You can't store the whole index in memory. So what has been developed.
Yeah, that's when data by also there was bigger spans, and so we store some.
Elasticsearch got pretty good at parallelizing stuff. So if you have 2-3 computers that they all manage the same index, it's get things in and out. But it's not feasible to have the whole index in memory. So you can cache some things if you want. I think in this homework 1, we did allow students in the past to pull all the tier values and store them somehow. It's up to you how, just to have it handy. But in practice, you can do that. You can do it for a query. You can say, okay, I have a query, and I notice this query is popular today, right? Something happened, right? So then I'm going to pull those terms from the query or related terms and pull all the inverted lists just to have them handy, because I'm expecting this kind of query and this kind of words to be asked a lot today, maybe. But to store everything independent of the query, that's hard. So we're not implying that the sparse matrix should be stored in memory. But for this document collection, you can, because it's not that big.
Okay. And again, so as a question is about this, so when you're actually doing Elasticsearch,
You can. I'm not sure that's gonna work well. I think people have tried that, and most people have success, easier success, because it's time pressure here. We have 2 days.
So I did,
They store it in advance. When they process the document, the script that processed the document, your script in Java or Python, counted the words and stored it separately in Elasticsearch.
I guess.
So I'm having another field in the body length or text length, and I'm just storing it there.
That will stop work. Or
That's
you
up to
can-
you. I mean, I don't mind if you have a text and you don't store the length, and you just pull the text and you say count the words or something. It doesn't matter how you do it for us, but I think I think from what I remember last year, most people find it easier to just count the words and store that number.
Because I'm doing the, getting like something on the phone.
But then you have to get the whole text back and count.
It's not text, I'm just adding, since already tokens, so each token.
Add the frequencies per document.
Anyway, I have to go
Yeah,
and.
but you don't need all the, see, for a query, you doing this at query time?
Yeah.
A query, you don't need all the frequencies. Right, so the whole point when you get a query time would be to work only with the query terms.
Yeah.
By trying to add all the frequencies, you need to put your hands not just on those query terms. You have to go over that document to see what other words are in there. I think in principle that's slow, but again, we don't grade that. If it works, you get the performance values, we count it. But I think the intention is to either I think the best thing is to store the document length somewhere in the index. When you process initially the documents, have a field value that says document length 300.
And we don't have anything in cosine if we're taking these scores as like weightage.
Elasticsearch has many built-in functions, but you have to implement it yourself.
Yeah, but these for the higher the scores, the better the.
It doesn't matter how you implement it. I think you can use a cosine in Java if you want. Or, I mean, I don't mind if you use a built-in function, but I don't want to use a Elasticsearch function. I want to get the scores
Yeah.
and then produce a similarity score. It doesn't matter if it's exactly TF, IDF, or cosine, as long as it's some sort of dot product.
Because it doesn't ask to be similarities, it just says some. Yeah, that is nothing.
So
but
I
a
think the
non-product.
TAs will ask you more for the representation, what are the actual values that document is represented by, the TF scores, IDF scores, TF, IDF, or copy TF, or whatever. The actual formula, it's more or less up to you. I mean, all those formulas are heuristics. If you change them a little bit, you want. We don't use the live. I have a website. So if you can, one of them can do it. Okay, or you can write it down here. There's a link there to Piazza, and you have to set up the whole share with us. Okay. I have here the rubric for algorithms. In my bag. There. Okay. Okay, so the other languages the other systems that we're trying to implement here are language models. We're gonna turn this off. And maybe you can take a look to see, to make sure that it's recording properly. So this is kind of one way of think about the problem. Language models, it's another way to think about the problem. here. In English, what is it that we want to do here? We want to say how, let's say, create, say, a query model. I don't want to say what model is first. Just say create a query something, representation model. And then ask for a document, the score of a document, D. It's kind of language model of D is how likely is D to fit the query model. Let's query the query model of Q. That's what we want to do in English without mathematics yet. Right? But we can do this. That's one way. We can say, how about we create a model of the query, but we also create a model for the document, and then we ask how likely a model of query matches the model of the document. Presumably, if they're very similar models, they're good. Now, you could say we actually did this for vector space models. We created a representation for the query and one for the document, and we have a similarity function that just said how similar those representations are. Except in here, by model, we mean language probability models. So the underlying mathematics of vector space models, it's linear algebra. Because a lot of the operations here come down to linear algebra operations, things like dot products, normalization, stuff like that. The underlying mathematics here is probabilities. So those models be more like, what I mean is more like probability distributions. So that's what we want to do. So first, let's kind of think how we, before we get into how to match things, what do we mean by a model? So here's one way to say unigram language model. If a document is W1, those are words. W2, I don't know, D, maybe 4. This relevant, I think last time we call it sometimes Y, yes. So sometimes it's R, sometimes it's double, sometimes it's Y. So I'm not doing anything yet with models. I'm just going to establish some things about words and probabilities first. What this is saying is try to take some of these ideas into mathematics. It's saying, okay, you have a document and you have some sort of relevance model or criteria or something that the users want to see, not defined very well yet. The way you can think of that document is a bunch of words. These are actual words. These are not TF counts. But they might be TF counts if I choose to implement as TF counts. These are the words in my document. And in here we can think of a document as a sequence, because that's what the document is a sequence of words. Maybe the order matters. But then the next immediate step, it's saying the probability of this sequence of words to be good is actually the product of every word to be good. Have you guys seen this kind of mechanism before? Where it says the probability of this whole thing, that's a document or an image or a vector or whatever, a bunch of events, cumulative events. The probability of these things to have a property is actually a product of individual probabilities for each one of them to have a property. We've seen this many, many times, right? How is it called? Independence. So this is an independence property. Most formally, I think you've seen it when you talk about random variables, right? We have these random variables. Sometimes they're independent, sometimes they're dependent. Some of them are more dependent than others. Dependency is not a black and white thing. There's a way to quantify how dependent things are. We can talk about conditional probabilities or entropies or things like that. There's a lot of mathematics developed into how to deal. Is that true though in language? So this independence, I'm talking about the property of a document being good. We didn't say what good is yet, but let's say we have some criteria for good. Is it actually a product of individual words being good? I think semantically, if you ask a linguist, somebody who studied languages and meaning and specifically translation, might say exactly like you react, get out of here, this is never gonna happen, right? Like, I mean, languages are complicated, languages are sophisticated, right? But let's not go down to earth. If I have a query like nuclear bomb, do you think I'm gonna match a document well? I don't even know what good means because a user put that query, I have no clue what he wants. He put that query, I get the query, but I mean, assuming he wants to know about nuclear bombs, but who knows what he actually wants. Good, it's a very vague notion in information retrieval because we don't know what good is until a human looks at it and says, yeah, I like it. Okay? So do you think I can match documents about nuclear bombs by just breaking into words and make a product? Would I? Do you think I'm going to have success with that strategy? I think I will. Because I think if things match nuclear and bomb, they're going to give high probabilities, match up high. Would it work all the time? Maybe not. But most of the time, if I have strong keywords, this might be okay. That's actually a property well known in statistics. Naive Bayes. Naive Bayes uses a lot of this property. It says, for something to happen, it's too complicated to model. This is called a joint together of variables. And model a joint is too hard simply because the support of the joint, if every one of those individual random variables has, say, 3 possibilities, not to mention some that are grades, A, B, C, D, F, there are 6 possibilities, or this could be age from like 15 to 45, and some could be numerical, like salary, many possibilities. But even if one of them has only 3 possibilities, and I have 20 random variables, what's the support of this joint? 3 times 3 times 3, right? I mean, if I have to consider all the possibilities of a joint, the number of cells that I need to estimate is big. It gets big very, very fast. It's a very well-known problem in statistics and machine learning. if you have data with a large dimensionality, there is no feasible way to estimate the joint. That's why when we estimate joints, we make either assumptions about dependencies like this. It says, to estimate this joint, you have to break it into components and assume independent. Or the other big way to estimate a joint is to make a modeling assumption, to say, this joint's gotta be a Gaussian function, or a Poisson function, or something that depends on few parameters. I just have to set these parameters, but then I force the joint to look like a Gaussian. You guys know how Gaussian looks like, right? So by imposing that condition, I'm allowing to choose different Gaussians, but it has to be a Gaussian. I'm not allowing this joint to be any other thing. Independent assumption has the disadvantage that it forces the independent condition, but it doesn't make a modeling assumption. It could still be anything. It doesn't have to be a Gaussian. Each individual component could be whatever it wants. So those are the two big things that I want to bring up first. That's all true for all data science, not just AI. Whenever we have a joint of anything that looks like random variables, it's infeasible to estimate that joint as it is from data. We would need way too much data. All the data in the universe, in atoms, could not satisfy a good estimation. So then we have pretty much two possibilities. Either we make a strong modeling assumption, we say this joint gotta have a parametric form, like a multidimensional Gaussian. And then we do the best we can to estimate those parameters. In a Gaussian, what are the parameters? Mean, sigma, in a Poisson, there's a lambda, so on and so forth. Once we make a modeling assumption, we do the best we can with maximum likelihood, say, to estimate those parameters. The other option is to not make a modeling assumption, but say there is independence among my variables. So I'm going to estimate each one of them separately. And that's okay because it's not going to force me to make any modeling assumption. Now, this is never going to happen in practice exact. No data will have an absolute independence property. I mean, even if you want to select such a data set, you're going to have a hard time. Things are simply not independent in nature. They may even look independent, but they're not. Like people say, two events, I'm going to get a good grade in this class, or I'm going to date that girl that I want to date, right? They look independent, but they're not. Because one going to affect each other in a hidden way that you don't see, right? I mean, that's obviously going to affect things, because the more time you put in studying, the less time you have. I'm just saying, even if you try really hard to come up with pure independence things, unless you generate with a computer an independent sample, very little data is actually independent. However, this trick works remarkably well, even if data is not independent. So you'd be surprised how well naive-Bayes work on things that you just know they are dependent. Yet, how many people in biology, and you read this paper about epidemiology studies or all kinds of statistics, they use naive-Bayes and it works quite well. And in machine learning too, it does. But it doesn't mean the data has to be independent. The way this is worked in theory, it says if the data independence, these are equal. It doesn't say that if the data is not independent, they are necessarily not equal. So if it's not independent, you can hope it kind of works. That's number one property about statistics that we have to know. It's going to happen a lot for us because everything with words going to have this property of dimensionality is huge to start with. I mean, you could say for d equal 20 or 10, maybe there is ways around because d is small enough, but for us, d will be so big all the time that we have absolutely no hope to deal with this problem. So that's one thing. The other thing is how do I do this with, say, let me erase the first part. How do I do this with a query? I want probability of a document given a query. So this is conditional probability. I could say I want this to be probability of the other way, query given document times the probability of the document divided by the probability of the query. Are we familiar with this formula? I think you've seen it before, right? It's called Bayes formula. Right? This is for general random variables. This formula is true all the time. Does not need any independence or any property. That's true all the time, simply because the product of this and this is the same as the product of this and this. So the explanation is that dq times d is the same as probability of qd times the other way, dq times q, which is who? This is probability of d and q as a joint. So both of those things conditional times the other one. You can think of, if I want a good grade in this class and date a girl, you can think of that process in two ways. Either first date a girl, and given that I date a girl, get a good grade. Or I could get a good grade, and given that I get a good grade, date a girl. Right? Either way you think about it, you end up with this, which is symmetric. Okay, that's the Bayes formula. And now, how do we deal with this? So we're gonna say we are in ranking mode, remember? So we care about, we allow ourselves to do all kinds of modifications mathematically to these things as long as the ranking doesn't change. Ranking of what? What are we trying to rank here? Documents given the query. So this thing, we can get rid of it. Because whatever that value is, P of Q, it won't going to change the ranking of documents, assuming it's a positive value, right? So let's say in ranking, that's the same as probability of Q given D times Q of D, right? How is this called in Bayes? Do we know? Huh? These are the conditional you want. This is the conditional we can estimate from data. This is a normalization constant, and this is a prior. So I'm going to say here, I'm going to assuming uniform prior. Over D. That means I start with all the documents being equally good. So that's just P of Q given D, right? Because now that's a constant. Is that true? Would Google assume all documents are equally good before looking at them? No. Looking at the content. Why not? What would be a better document than another document for Google before I look to check the keywords? Because I can still check the keywords here. The prior means before looking at the content. What would make a document for Google better than a different document?
The resource it comes from. The source.
Where it's coming from? What else?
The visits, number of times it has been referred to.
What else?
Duration. How long that.
So when you say number of times or what?
So how many times have people previously referred to the
People seen it, you mean clicked on it.
Yeah.
But what else? Before all this is recent stuff. Early Google, what did they look for?
Length.
Size.
Length of.
No. PageRank looks at what?
PageRank?
How does PageRank rank things independent of content?
Reference? Links?
The links, right? They look at the link analysis. They don't look at the content. The link analysis is simply what document points to what other document, build a graph on that, and use a graph Markov chain property to come up with PageRank scores. That gives a very strong prior before even looking at the inside the document. It's true now that they use more clicks and IPs and other things, but the early version of this prior was simply importance given by links, right? So that's definitely not true in practice, but let's simplify things here. Now, who's my query? My query is a bunch of words. Word 1, word 2, and word 3. I'm going to say just 3 because it's a simple query. It doesn't have that many words. So now I'm using that sort of stuff in there. How do I do that? So I'm going to say independence. The query has 3 words. And what is this going to be if the query is a sequence of 3 words? If I'm applying this independence model here. It's going to be the product of all the words in the query, of the probability of that word in the document. So this is the probability of word W in document. Okay? Now I made a lot of assumptions here. Again, do they hold conceptual in data? Of course not. Do they work in practice? Yeah. We use them all the time. So don't stress too hard if the theory doesn't really match what we're going to do. But that's how we get to these formulas. So that's the basics of language models. If I really want to know, I have a query, what documents are good for that query. That can serve as a scoring function, right? This produces a score, I get a score, I rank by that score, I get my function, right? Well, I do kind of something like that. I have to take care of the query, maybe process some values in there. There's some steps here that I kind of skip. You have to implement those steps. But then, I need this. This is effectively P of W over D for all W. This is effectively a language model of document D. This having those probabilities of the words, that's probability, right? For a document, that's a language model of that document. So, like in vector space models, there is the implementing of the function, which is, okay, if I have such a model, how do I rank things with it? In the vector space model, we had this process of cosine similarity, where we do the dot products normalized by the lengths, the out process score. In here, this is not a dot product, right? I mean, let's make this observation that's easy to see. In the dot product, every value of a word in a document that was a TF count or something like that did not get multiplied with another value of a word of that document, right? In a dot product, things get multiplied with what? If I get some representation of the document, some values, they don't get multiplied with each other. They get multiplied with query values, which are typically 1 or 0, because they only miss it. It's only the word there or not. So this here is more like a sum, right? This, if you take the queries as 1, 1, 1, 1 representation of the words, this dot product is literally a sum, more or less, of the document word values. This is not a sum. This is a product, but we can make it into a sum, yes.
So I'm looking at the theory and then I'm thinking about how I would actually do it.
How do you implement this?
Yeah, and then I'm thinking that the probabilities would probably be low. And if they're low, then it's floating point, and then floating point does kind of funny things.
So he's worried about numerical issues.
Yeah.
This, if the probabilities are 0.0000 something, which might happen in a document. We didn't talk about how to get probabilities yet, right, from documents, but maybe not so high. Computers have a problem with low numbers, especially when it gets multiplied, right? Because what happens with the decimals, if a number has, say, 3 zeros after the decimal, and the number has 4 zeros on decimals, when I multiply them, how many zeros I get after decimal point? 7, right? So how many words am I going to multiply here? They're going to be very far away from decimal point. Now, computers also have a way to do arbitrary precision in some languages. So I can set a precision to whatever number I want. If I want to do that, if I don't want to use standard integers or floating or double values, I could get huge precisions. Like physics needs a lot of precision, so they have special built languages with arbitrary precision. And some other languages, in Perl, you can define arbitrary precision. It takes more time to do the operations. But this is not how people multiply things. Actually, if you know a little bit of machine learning, how they deal with this product of probabilities. Take logs. Right? So logs will solve that problem, I think, because if I take logs, I won't get too far away, and then instead of multiplications, I get addition. So let's say this is another ranking equivalent to say, in here, I could just say, how about I do, the product becomes a sum, right? Sum over W in the Q of the logarithm of the probability of this in the document. I'm sorry, I wrote sometimes D, big D, sometimes small d, I mean document. Okay? So that's ranking equivalent, right? There's still some problems here. Logarithms cannot be taken off 0, right? I mean, if what he was saying gets really, really close to 0, even the logarithm gets kind of undefined at some point. But maybe we don't get that close to 0. In fact, it will be useful in a lot of data scientists, not just IR, to prevent things getting close to 0. Every time you have probabilities and multiplications and operations where 0 is not a neutral element. In addition, 0 is a neutral element. There's no danger in having 0 in an addition. If it's 0, leave it 0. But in multiplications or logarithms, you don't want your system, for whatever reason, no matter what the probabilities are about, words or images or something else, you don't want to let those values get too close to 0. That happens in probabilities, also happen in linear algebra operations. Determinant, if you remember, it's 1 over determinant dictates some properties of the inverse matrix. If that determinant is very small, the matrix is very close to be singular, even if it's not 0, that inverse matrix could get way out of the space that you want, so create a huge variance. People know what I'm talking about? So if you deal, for example, with Gaussian functions, in a Gaussian formula, there is sigma at -1 somewhere in there. If that sigma at -1 is a matrix, because it's a 3-dimensional Gaussian, you don't want to take the inverse without checking the determinant of the matrix, because the determinant happens to be close to 0, especially in big matrices, it might be close to 0. Then taking the inverse, while a correct algebraic operation, it's going to give you a totally undesirable result. So what people do, they look at that sigma and say, hey, I don't want you to be close to 0. So they do all kinds of tricks to increase it, like increase the diagonal. When a matrix increases the diagonal, I can get out of 0 space quite easily. In here, I can easily prevent all those probabilities to be close to 0. Everything that's smaller than an epsilon, I make it epsilon. So I fix an epsilon, so it's 0.01, and I say nobody can get below this epsilon for any reason. Make sense what I'm saying? So in systems that have products or logarithms or inverted matrices, we don't want to let things arbitrarily close to 0, even though that might be conceptually correct or mathematically correct. When we work with computers, we don't want to do that. So that's a good reason to not let things go to 0 here. There's some other good reasons for that in our particular IR system, language models. That's not the only reason to prevent 0. But let's recap what we have. What we have so far is, like in vector space models, a strategy for how to score things, right? We get the query, we get the words in the query, and we say, now I have the words in the query, I'm going to multiply the probabilities or sum the logs of those probabilities for those words. Presumably, I'm only dealing with the ones in the query, right? Because again, I have 50,000 words of vocabulary in my index, but if my query is nuclear bomb, can I just do this thing by only looking at the words nuclear and bomb? I'm asking. Do I have to pay attention to anything else? I asked this question an hour ago for vector space models. Can I just deal with the words that are in my query and ignore everything else? Can I do the same here?
Yeah.
Nuclear bomb, just don't worry about anything. Get the nuclear inverted list, get the bomb inverted list, and whatever I need, and do my operation based on those things, and be done. I don't need to worry about what else is in the index. That's why we want the index to return the inverted list for that term and nothing else quickly, because even though I have many words, I may only need 2 or 3 words to answer this query and score this document, right? Again, I'm not going to the implementation details, because when you go home and you implement this, hopefully very soon, it's due Wednesday, remember? You're gonna hit some hiccups, okay? It sounds really easy when he said it in class, and now it doesn't really work on my computer. Okay, but we didn't talk about this. What is this? In vector space model, we have few options for this. I think they erase now, the TF, TF-IDF, or copy TF, and all those properties. In here, we have to estimate these word probabilities from data. Okay, so how do we do that? How do we look at it's just a different representation of documents, right? It's not TF values, it's something else. What is it? So what is probability of W given D? Let's write it in English. Probability of word W in or from document D. TF of W in D, that's the count, divided by document length of D, right? Okay, we'll call this the foreground, probability foreground. That is the direct estimate from data. If I get only one document, that's what I'm going to get. So there's a problem in taking this directly as the probability and working with it. Maybe more than one problem. What is it? It's what I just said a minute ago. I'm going to get a lot of zeros if I do this. For many words, in many documents, I'm going to get a straight zero. That's one problem. That's not the, statistically, I mean, that's true for words and documents because words are very sparse in documents. But even if I don't have a sparse data set, that's still a problem sometimes in machine learning or in data in general. Apart from sparsity, for us, it's a huge problem because if you look at the term document matrix, 99% of it is 0. And by that estimate, everywhere you have a count 0, you get the 0 probability. Definitely bad. We just said a minute ago, we don't want things to get arbitrarily close to 0, let alone exactly 0. But there's another problem in estimating probabilities. Let me bring up something that you probably have seen in high school. I have a coin, and it has two faces, heads and tails. And that coin may be biased. Bias means heads is more likely to show up than the tails. It's not a 50-50 coin, right? When I have a die has 6 faces, and I fake the die, 6 is more likely to come than 1, 2, 3, 4, 5, right? The thing is, I don't know how biased the coin is. I know the chance of throwing the coin and coming up heads is bigger than the chance of throwing the coin and coming up tails. But I don't know that chance. I know maybe it's not 50-50, maybe 60-40, maybe 70-30, maybe 80-20, maybe 100% to 1. How can I estimate that probability with the coin? I have the coin in my hand. I want to know what's the chance when I'm throwing it up to get a head. I start throwing it, right? throw it. Suppose I throw it a few times. Suppose I throw it. So that's number of heads versus number of trials. Suppose I throw it 3 times and I see 1 head. If I estimate things this way, what's my estimate of the probability of heads? 1 over 3, right? So the estimate is 1/3. Suppose I keep throwing the coin, and by the time I hit 10 trials, I see 4 heads. It's 4 by 10, right? Suppose I do 100 and I get 35 heads. 35 by 100, right? Suppose I do it 1,000 times and I get 312 heads. So now it's 312 divided by 1,000. That is the raw estimate of probability from data directly by throwing the coin, right? It's very similar to looking at, I'm assuming this word randomly can appear in a document by reading new words in the document. I'm throwing the coin and I'm seeing if that word I'm looking for shows up or not. There's a hidden thing here that it says this value is much more believable or trustable than this value, because there's not enough evidence here, and here there's a lot of evidence. You can see this by characterizing the possible values. So I got here 1/3, right? But if I only tell you I throw the coin in the air 3 times, I don't tell you the number of heads. I just say 3 times I throw this coin. What are the possibilities for the number of heads if I throw it 3 times? 0, 1, 2, 3. There's only 4 possible choices. Independent of what that coin was set up to do, there's only 4 possible outcomes of this estimate. How many outcomes are here? 1,001 outcomes. So this is a much more granular or refined estimate because it can estimate quite granular, the actual probability. Okay. This happens a lot in science fields, of course, but even in things that maybe people don't realize immediately have to do with science, like casinos, or when you play cards. The sample size, what you're looking at, or when you do a polls for elections or something like that, it matters the sample size you have to produce a validity or confidence of the estimate. So all the statistics will come with something like variance, confidence intervals. That will not just be an estimate, but what the margin of error or confidence associated with it. Good. So we know that. So what will make a big sample size then? What's the equivalent of throwing the coins a lot for me? I'm now back to looking at documents. Long documents would be a huge sample size, as opposed to short documents that are a small sample size. So a long document may not just be a document, may be a whole Wikipedia collection, right? I mean, when I say long document in terms of a sample size, I really mean a large body of text. A short document might be just a tweet. Actually, it's a well-known thing. People who do research on blogs, that's been very hot for a few years now. Blogs and quick posts, people post very short things. They have a problem. Mathematics don't work at all on that stuff. Because of this reason, you can't estimate any probability from tweets. It's too short to have good, reliable estimates. And not just that, people are inconsistent even among themselves. When they write something, they sometimes write the term, sometimes abbreviate it, sometimes write in a different language. It's very hard to estimate probabilities in an inconsistent posting. So this kind of stuff works very well on Wikipedia documents, which are written formally, most of them, edited, correct English, and long enough, as opposed to things like tweets. But then still, nevertheless, that's a foreground probability, just like I have here a raw estimate. What else can I have is a background probability. I'm not sure Well, let me see. I'm going to get the background probability, which it's exactly the same thing, but not estimated from one document. It's estimated from all documents. So in here, I'm going to have the total count. I think it's TTF, total count of word. I think that's called TTF, divided by, it's not document length, is the number of words in collection. That is the sum of all DL values. When I say number of words, I'm including the duplicates. Like if the word Virgil appears 5 times, that counts as a 5. If I say vocabulary, that's every word included once. It's like a dictionary of all the words that I've seen. But the total count of words, the sum of the document length, is just simply all the words I've seen in my collection by concatenating all these documents. In your case, 85,000. In Wikipedia case, is 4 million. Okay. So what's the advantage of estimating this not in one document, but in all documents? Obvious advantage, sample size would be much bigger. What's the disadvantage? This is not specific to a document. It's just specific to that term. It's how many times the word China appears in my collection altogether. So that's why it's called a background probability. It's like a prior for that. That's not document here, they just put the W. So I can have a foreground probability and a background probability. That's, by the way, not the only way to get the background probabilities. Sometimes people use background probabilities that are pre-computed. In other words, there is a dictionary that says, here's a word, and here's its chance to appear in English. It's been pre-computed somehow from a large body of documents, not, because you can do it from 85,000 documents, but other people can do it from like billions of documents. In fact, it's well known for most words what is their chance to appear in English language. It's not something that it's well understood. Again, the disadvantage is this is not for a document. This is a prior across. Right? So what do I do with those values? Or what do I do with this value? I have to take into account the raw evidence. Somehow, obviously, how many times that word appears in documents gotta matter somewhere. What people do, it's something called smoothing. So smoothing probabilities estimates. We're going to say the probability front, or sometimes we're going to call this raw, is the DF by DL. That's essentially count by sample size. So that's our base for the estimate all the time. But then, how do we do this smoothing? So one option, it comes from Laplace, French mathematician. I think it was French. Here's what this guy said. The output probability should be TF plus 1. I'm looking at this formula here, divided by DL plus the size of the vocabulary. Before we get into it, I want to do the same thing in here, just to give you an analogy. What would be the Laplace here by applying the same methodology? Would be the count, the number of heads, right? Divided by the number of trials, plus 1 at the numerator, plus what's the vocabulary in a coin flip? So when I flip a coin, the vocabulary, the number of possibilities is 2. When I look at words, the number of possibilities to see the next word, assuming independence and nothing semantically, the chance of seeing a particular word is with uniform prior 1 over V, right? Because I have so many words V in my vocabulary. So what's the magic around this Laplace formula? So first of all, it says if you have no evidence, what you left with?
Yeah.
A prior. That's uniform prior. So that's the first thing that we have to notice here. In both cases, if we have no evidence means who is 0? Mm-hmm. No evidence means no trials. You can still have a lot of trials and 0 heads, right? We can still look at a long document and not observe the word nuclear. Evidence means we don't have words at all, or no trials at all, right? As soon as we have trials, we have evidence. If we call people up who you're going to vote for, we have evidence. Maybe nobody going to vote with, I don't know, some particular candidate, right? Let's say that, for whatever reason. That doesn't mean we have no evidence. We call people up, nobody wants to vote with him. But we do have evidence, we call them. No evidence means we didn't call anybody, we don't know what people want to vote with, okay? So, no evidence means uniform prior. That's happening in here. Of course, in languages, uniform prior is no good. Certain words are much more likely to appear than other words. Assuming a uniform prior is probably not going to take us very far. What else this is controlling here? How this function behave when evidence starts coming up? Okay, so I'm going to say, let's take a raw probability. It's, let's say, 1/5. So I'm going to assume that's the actual ratio of estimation, but at different levels of evidence. So I'm going to plot here the Laplace output versus the evidence, which is number of trials. Now, I'm assuming the raw probability is always 1/5. So if this is 0, the head count in here will be 0. So I'm going to write this down as heads versus trials. This could be 0, 0, right? 0, 0 is undefined. I can't really divide 0 evidence. But if trials is, say, 10, what should be the heads to get 1/5? 2. So that will be a 210, right? And if trials is 30, that might be a 6, assuming I get the same ratio. And if this is 100 trials, that might be a 20. So how does this Laplace output work? And I get 0, 0, what's my Laplace function going to do? 1/2, right? Because that's 1/2. When I get 210, what do I get with Laplace? 3 by? How much is that? 0.25? So the output here would be 3, you say 3 by 12? Okay, so that's at 0 on here, this point. How about in 630, what do I get? 7 by 32 is how much? Is it higher than this or lower?
Less than 0.21.
Less than this?
0.21.
7 by 32?
Yeah. Yeah, that's, yeah. 0.21.
0.21?
0.21.
Uh-huh. Maybe it's in here somewhere. And then if I get 20 by 100?
Still low.
Even lower, right? 21 by 102. So what's going to happen with this function? This function is going to look like this, right? And when I get enough evidence, what's the limit? 1/2 won't matter, that's my point. When I get enough evidence, it's just going to be heads by divided by the trials. This 1/2 becomes irrelevant. But with the more I get less evidence, the more the 1/2 matters more. Right? So I think we want the same thing to happen here. If we get no evidence, we want this to be close to a reasonable prior. I'm saying reasonable prior because 1/v may not be so reasonable. But if we get a lot of evidence that corresponds to long documents, we want the prior not to matter. We want to be TF by DL. In Laplace, if I use 1/2, what characterizes muting functions in general is the speed at which they get rid of the prior. So in other words, how much evidence do I need to kind of the prior to become insignificant? And I can control that. I can add a little variable here, 1a plus 2a, when a is a constant, a is a parameter. This a is going to control the prior. The prior. The plot I have here is for a equal 1, right? How do I make this prior more important? It's still 1/2, right? Because 1a divided by 2a, it's always going to be 1/2. But I want the prior to be more important. I want the prior to contribute even if I get evidence. What do I have to do with the a? Increase the a. So if I increase a, I make a equal 100. I still start at 1/2, right? Initially. Because with no evidence, it's 100 divided by 200, it's 1/2. What's going to happen with this plot? Eventually, we'll still go to 1/4 or 20%, whatever the heads by trial is. But what's going to happen with it? Go much slower. So this is a equal 100. And if I want the prior to be going away very fast, what do I have to do with this a? Make it very small, right? So suppose I make a be 0.1. I still start at 1/2 because when I have no evidence, it's still 1a divided by 2a, that's 1/2. But the plot will go very quickly to 0.2 or whatever the ratio is. So this is a equal 0.1. Make sense? So I can control, this is the same phenomena, but I can control the strength of the prior. So that's what you have to do in here. I'm not going to say what, because that's up to you to go home and figure it out. But you have to think, is 1/v, in terms of size, what's v? Okay, vocabulary. So how much is v for? Did you index? How many words did you get in the index?
222, almost
200 words? I think it's a lot more than that. How many?
200 by 2k. Like
2300? 23,000.
Yeah.
So if I put v 23,000, is that going to be what sort of prior? Is it a weak prior or strong prior? Like how much evidence I need to effectively get rid of it?
About the same. Or
Really?
more.
So let's take a word like, I don't know, not nuclear, that's too specific. A word that might appear. So let's consider a word that has TF around 4, talks about algorithms, say, in a document length that, what's the typical document length in this collection? 365. So let's say we call this typical, right? So then what this function is going to look like if these are my values? 4, let's do it here, the Laplace output is going to be 4 plus 1 divided by 365 plus 23k. Is that what you say? I specifically don't want to say good or bad, but I want to ask you, is that the formula that we want to interpret? Again, you want to count for the prior somehow, that's a good idea, but you want to address the sensitivity for typical values. If I see a word out of 365, versus suppose in a different document, the same word appears not 4 times, but 3 times, or 2 times. So in a different document, I have TF equal 2, and maybe DL very similar. It's not 365, it's maybe 287. Then I get 2 plus 1 divided by 287 plus 23K. I think we need to figure out a little bit if that's the values we want. Again, keep in mind that this is theory. Theory says how many possibilities you have of a word. 23,000. So that's V, 23,000. Just like it says in here, how many possibilities you have for a coin to flip? 2 possibilities, so that's a 2. Theory doesn't have to match the practice. So I think we should come up with a V. Maybe not that V, 23,000, but a different one that works better here. By looking at the sensitivity of these plots, you know, how much we want TF increase from 2 to 4 to contribute to my formula, which is of course logarithm of, right, remember we take the product and then we make it into a sum of logarithms. So if I am to take logarithms of this value, 3 by 24,000 versus 5 by 24,000, those logarithms, once I take the log, that's a contribution of what I have in my index, right? Just to be clear, I'm here, right? So now for this word that I have there in 2 documents, and one document will be logarithm of 3 divided by 24,000. That's going to be the contribution to the sum. Because every document has a sum of 3 words, right? I'm fixing one word, and I'm saying for that word, my contribution here will be logarithm of 3 divided by that. For the other one will be 5 divided by that. I can look at this logarithm and say how sensitive things needs to be. I can control with that size of V, even though it's not exactly the vocabulary size that's in the collection. Okay, so that's one thing. Another thing that we can do here, so that's Laplace smoothing. There's a large theory with integrals about Lagrange smoothing derived from principal mathematics. So if you're interested in that, I can point out to 3 pages of integrals that derive this formula. But I think it's much easier to understand in the way we explain it. Without evidence, you choose the prior. Maybe for a coin, you get half and half because you don't know anything. For other things, maybe you want to use a different prior. Like for words, maybe a uniform prior is not necessarily the right thing. But Laplace uses a uniform prior. And then we can control the strength of the prior. Like how much evidence do we need until we get rid of it, effectively. Another way to do this